Hi everyone, welcome to lecture number 13 of Calculus 3. This is on change of coordinate transformations. This is in reference to computations of double integrals, or integrals of functions of two variables. So let's start though with some motivation from Calculus 1. Let's consider the following situation. So consider the notion in Calculus 1 of a U substitution. So one of the main tools that we use in integration in Calc 1 and then again in Calc 2, of course, is a U substitution. And it works as follows. So let's suppose that we have an integral from a to b of f of x dx. So this is a definite integral. And we want to compute this by changing variables, right? And so what do? Well, we let u equal some function of x, right? And then we do a couple of things. We have to make a couple of computations to make sure that this is going to work. Number one, we have to change our limits of integration, right? So we have to determine the new limits of integration. So u of a, we'll say is capital A, but we have to compute that, right? And then u of b is going to become capital B. So there's computation of each of those. And then the other thing that we have to do is we have to determine the new differential. So we have to know how to replace the dx, right? So du becomes du by dx in one case, and then we can also rewrite this, right? So this is how we usually do this though, right? We make sure that we have the right pieces, we make this change of variables, and we plug in, and when we use this in Calc 1, we're making a pretty straight substitution. And we just have to make sure that we compute from there, right? And so the whole idea here is that if we have two kind of number lines, we have our u number line, and we have, so this is really like our domain of our integral, right? The x1. Then the integral on one hand, the one that we want to compute is working over here, right? But when we make our transformation, u of x, what's it actually doing? It's taking this and it's mapping it to this, right, to this space, u equals u of x. And so over here, the interval might be extended, but it also might be compressed one way or the other, right? It could be exactly the same, but it's probably not. All right, and so now we're computing our integral on the smaller interval. And so we have to compute how the element, right, the length element changes as we move between these two. But in reality, what are we doing? We're pulling back over to this space to compute the integral, but we want to get our answer back in this space, right? So what we need is we need to know what is our transformation. X equals x of u, right? So the inverse transformation. And so this is the whole idea now, right? So when we take the inverse relation or the inverse transformation of the one that we wrote down, this is the one that's kind of, most obvious based on the form of our integral, then we can do this, right? So the inverse transformation, it's going to be the following. It's going to be exactly what I wrote here. So x is going to be equal to x of u, and then we just straight substitute that in, right? And on the other hand, dx is going to be now equal to, it just flips, right? dx by du times du. All right, and so when we plug these into our integral, along with these boundaries, so this is actually what we want here, right? Along with these boundaries, what we end up with then is that our integral from a to b of f of x dx is actually going to be hopefully easier for us to compute, but it's going to be transformed, and then again, hopefully for a reason that's going to be helpful to us, but it's going to be transformed to the integral from capital A to capital B of f of x of u. So that's now a function of u times dx, but dx has got to be in terms of u as well, right? So it's then multiplied by dx by du times du, the derivative dx by du times du. Okay, so as long as our transformation is invertible, then we can do this, right? So this is the idea from Calc 1. So two major things happened here, right? It's two major transformations happened. I mean, there's one transformation, but there's two major parts of it. So let's write them down. Number one is that the domain changed, right? So we mapped the domain. We're actually thinking of this as going in this direction, right? But we mapped the domain, the way we thought about it was going this way, right? We mapped this domain, the interval from a to b, to the interval from capital A to capital B. And then the other transformation that we made, the major transformation, was we transformed the differential, right? The differential had to change. The coordinates changed, but also the differential changed, right? So the other major transformation was that dx mapped to du, which is equal to this derivative, dx by du times du. Whoops, this is dx, sorry. It mapped to the transformation, so dx equals this, right? But it mapped to this transformation. This differential, I should say. The transformation mapped this differential. Okay, so the whole point of this is that we now want to consider how does this work in Calculus 3. So if our domain is two-dimensional, what has to change, right? By the way, remember dx is measuring a tiny, tiny, tiny length element, right? So a tiny change in length. And so that's what this has to measure as well, right? dx by du times du has to measure a tiny change in length. So now in Calc 3, we're talking, instead of length, we're talking about area, right? We're talking about tiny changes in area. So the situation in Calc 3 is as follows. All right, so now in this case we have a couple of things going on. So we have our domain is now a subset of R2. So I'm going to draw just a blob here. This is our domain. We'll call this one R. This is the domain that we want to compute our integral over. All right, and so what we're going to do is we're going to pull that back to a domain. So this is going to be like a UV plane in general, and this is going to be our XY plane in general, and a domain that's a little bit nicer. So maybe that's not perfect, but the idea here is that this is going to be a different domain, which we'll call S in the UV plane. And our transformation is going to do a couple things. So it's going to go this direction, just like the one that we ended up using up here. This is going to be our transformation we'll call T. And it's going to do a couple things. It's going to map this domain S onto R. So R has to be equal to T of S. Okay? And it has to be invertible. So we have to be able to go back this way. So T inverse has to exist in this direction. All right, that's the major, these are the major, at least, building block things that we need to worry about here. Now let's write down some formulas for them. So in general, the inverse map here, T inverse, is going to be kind of the one that's obvious. So just like we usually, when we do an integral in Calc 1, we're able to write down u equals some function of x right here, right from the get-go here, right? So it might be the same case in Calc 3, where our T inverse is actually going to be a function or a transformation which tells us how to get our u from x and y and our v variable from x and y. So a transformation from R2 to R2 is really a combination of two functions of two variables. It's going to tell us how our u variable depends on x and y and how our v variable depends on both x and y. All right. But again, the transformation that we're going to work with the most is going to be this transformation T. This is going to be, again, we'll see when we do examples, but T inverse might be the one that kind of seems the most obvious to how we write down the formulas, but T is going to be the one that we need to actually work with to compute things, right? And T is going to be the following. So it's going to then tell us how to get x back from u and v, and y as well from u and v. Okay? So that's akin to changing the interval. That's how we're going to change the domain, right? We're going to change the domain by plugging in u and v. We'll get back our x and our y. So we can just put this into our integral now and change the variable to u and v by inserting these two functions, right, for the map T. We do need to know, though, how the area element changes. And so I'm just going to write down this definition. But the change in the area element is given by something called a Jacobian, and I'll write down some formulas for it here. So the change in the area element is given by the Jacobian, and just like our Hessian, the Jacobian comes in two forms, a matrix form and a function form. So the Jacobian of the transformation, so transformation T, and it's given by the following. So there's a matrix form, which we're not going to, it'll be part of the definition here, but I'm going to write down the function form. So the Jacobian, J of uv, I'm going to call this. So this is a function of u and v that explains how the area changes over here, depending on u and v from back here. Okay, so j of uv, this is going to be defined as the determinant of a matrix, and the matrix is going to be the partial derivatives of this transformation. So it's going to be dx by du, dx by dv, dy by du, and dy by dv. Okay, and so this is the matrix of partial derivatives of the two functions in the transformation. The determinant, of course, is like this kind of crisscross product slash difference, right? And so it ends up being the function given by dx by du times dy by dv minus dx by dv times dy by du. Okay? And so this is the Jacobian of our transformation, and what we end up with then is that the area element changes according to this function. So delta A, the area, right, which is equal to, in rectangular coordinates, delta x times delta y, this is going to be about equal to j of uv at some test point, put stars here, right, always test points when you have deltas here, times delta u times delta v. So that's how this is going to work. The Jacobian, this function right here, is playing the role of the derivative dx by du up here. So this whole function right here plays the role of that single derivative from the Calc 1 or 2 perspective. And so, of course, what we end up with then is that in the limit, our dA, our area element, is going to be equal to this j of uv delta u delta v. Okay? And so this is the key. So our integral now transforms. If we have a double integral over a domain R, all right, of some function f of xy dA, then what's it going to become? Well, it's going to become the dA, I'm going to put dA of xy here, all right? So you could write this as dA of uv. So I'm going to write it that way, actually. It becomes, we're going to transform this to the double integral over s of f of x of uv, right, comma y of uv. So now the independent variables are u and v times the Jacobian of u and v times dA in the uv sense here, right? So this dA is probably going to be du dv. Whoops, I put deltas here. This was supposed to be d's. All right, but this is supposed to be d's. So du dv. All right, so this is how we're going to compute this. And again, we can, if we go back up here just for a moment, we could rewrite this transformation here, t, as a transformation that depends on u and v and gives back x and y. Right, so we could write it like this. And then we could replace this inside with just t of uv. Right, so this could be written as double integral over, so the double integral here is going to be of t inverse of r, right? So t inverse of r, that's our s, of f of t of u and v times the Jacobian of u and v times dA with respect to uv. All right, so that's all symbolic stuff right there, but let's do a couple of examples now where we actually look at the transformations and compute the Jacobian and see how they work, and maybe even do an integral or two here. So our first example, let's look at the following. We'll do this one together. So for this example, let's find a transformation and a Jacobian that takes us between these two spaces here, these two domains. So here's the scenario. Over here, so on the right hand side, we'll start with this one. Let's say we have an elliptical domain in our xy plane. So let's say I'm going to make a perfect ellipse. Maybe not. There we go. And that's a circle. Now it's an ellipse. Let's put it right there. Okay, so let's say that this crosses the y-axis at a height of 2 and the x-axis at a height of 3. Okay, so there's an ellipse, and this is going to be our domain R. So we'll call this R. All right, so this will be R. And then we want to transform this, though, to the following. In the UV plane, this is going to be S. This is going to be a rectangle over here. So it's going to be a kind of long rectangle like this. It's going to go from 0 to 2 pi in the U direction, and then just 0 to 1 in the V direction. And so this will be our S. All right, and so the transformation has got to go this way, right? So R is going to equal T of S under whatever transformation we come up with here. Now, I've chosen this very specifically here, right? So I'm going to write out the equation of this ellipse in its rectangular coordinates. This one passes through x equals 3 and y equals 2. It's centered at the origin, okay? So its equation, the equation of this domain, is going to be that x over 3 quantity squared plus y over 2 quantity squared should be less than or equal to 1. Okay? So that's going to be the equation of the ellipse that passes through these points on its major and its minor axes, and then fills in the whole space, right? That's the less than or equal to is going to fill in the interior of that ellipse. So that's R. So this is the equation of R. Now it becomes pretty clear how we want to parameterize this, right? So it's going to go as follows, right? So we're going to, basically we're just parameterizing this. If you think back to Calc 2, parametrizing. If you think back to Calc 2, we just want to make this be like R cosine theta and this be R sine theta, and then we can do it, right? So we'll set x over 3 equals R times cosine of theta, and y over 3 equals R times sine of theta in general, but we want to make sure that this goes into our u and v coordinates, right? And that we solve for these explicitly in terms of x, right? So I'm going to actually put like quotes around this just because we're thinking, and at this point we're thinking back to Calc 2 and parameterizations. We need to multiply by 3. This one's going to be 2. It's got to be this, right? Y over 2 should be R sine of theta. So with whatever's inside here. This one's cosine, this one's sine. So we want to switch this so that the R, the role of the R, is played by the V axis, right? And the role of the theta is played by the U axis. So what this ends up becoming is x equals 3 times V times cosine of U. And y is going to be equal to 2 times V times sine of U. All right, and so this is our transformation. So this is the transformation, T of UV. That takes the rectangle and maps it to the ellipse, actually. It goes in that direction, right? All right, the other part of the question was that we want to know what's the Jacobian of this transformation. So how does the area change, right, after going through this transformation? So how does the area change? So let's compute. We need to take the derivatives, right? So we start with this matrix, what we can call like a J hat or something. But the matrix that we start with is dx by du, dx by dv in the first column, dy by du, and dy by dv in the second column. And we just compute. So dx by du, derivative of cosine of u with respect to u is minus sine, right? So this is going to be minus 3v sine of u. dx by dv is just going to be 3 cosine of u, right? And then we take the derivatives of the y. So dy du is going to be 2v cosine of u. And then the derivative with respect to v is 2 sine of u. All right, and then our Jacobian is the determinant of this. So the determinant is going to be minus 6v sine squared u, right? Minus 6v cosine squared u. This becomes minus 6v times sine squared u plus cosine squared u. And so this then right, is just minus 6v times 1. Yep, so it's negative in this case, and that's because the roles that we've kind of used, the usual roles for if we think back again to Calc 2 of the r and the theta, we've kind of reversed them, and the u is playing the role of the theta, and the v is playing the role of the r, so we've changed the order of these two. But that's okay, so this is a negative Jacobian. What we end up with then is that our dA for this function is minus 6 times v times du dv, or dv du. In either order, it's fine. Okay, so this will be the area element, and this is the Jacobian itself, just this function, minus 6v, negative 6v. All right, so let's take a look at another example now, where we actually want to use a transformation to compute something. So for this one, this is going to be item number 4 or 3. This is going to be item number 4 for us, right? So item number 4, we want to compute the following integral. So evaluate the following integral. It's going to be the double integral over r of e to the power x plus y over x minus y times dA, where r is a trapezoid. So we'll say the trapezoid. I'm going to describe it now. So it's the trapezoid with the following vertices. So the vertices are going to be 1, 0, 2, 0, 0, negative 2, and 0, negative 1. All right, so trapezoid is quadrilateral. We just need to define the 4 vertices. So this is going to be, I'll get this started, and then I'll give you a moment to try to work it out yourselves, and then we'll check back in to finish it. But to get it started, though, we want to first start by sketching the domain R. We want to do this by a change of coordinates, so by a transformation. But let's plot these vertices here. So 1, 0 is here, 2, 0 is here, right? 1, 2. 0, negative 1 is down here, and 0, negative 2 is down here. And so our trapezoid looks like this, right? It takes the coordinate axes and then fills in kind of this diagonal here. So this is our R. Now what we want to do is transform this, right? So here's what we end up with, u and v. We need to think of a transformation here, though. So we need to try to come up with a transformation. One thing that we can notice is that these two, the bases of the trapezoid is what they would end up being, right? These diagonal bases. These are both given by pretty nice equations, right? So this one is given by, let me write the equation here, but this one's given by, it's got a slope of positive 1, and it's got an intercept of negative 1, right? So this is y equals x minus 1. Same thing with this one, right? This is a slope of positive 1, but an intercept of minus 2. So this is y equals x minus 2. All right? And so what this ends up being then is we can write this, transform it yet again, and write it as x minus y equals 1, just by rearranging, right? By subtracting the y over, adding the 1 over, x minus y equals 1 for this one, and this one is x minus y equals 2. All right? And the reason that I've written it like this is because we can now go back to our integrand and see, all right, x minus y shows up as a variable, right, in our integrand. So we can set one of our variables equal to x minus y, and then just based on the form of the integrand, we can choose to set the other variable, the equation, equal to x plus y, right? So we can write something like, we can set, let's say we want this to be u over v, right? We can set u equal to x plus y, and then v equal to x minus y. All right? And it doesn't really matter which one you use there. But now what it's going to do is in the v direction, our entire trapezoid is going to change between 1 and 2, right? So it's going to go from 1 up to 2. So it's going to be bounded between horizontal lines here, right? So that's fine. Now what we need to do is compute the other endpoints, right? So you can find the u values of the other endpoints and then plot the trapezoid over here and then compute that integral with your change of coordinates. So I'm going to give you guys a few minutes to work this out now, but this is basically, we've written down the transformation. So I said set these equal to, but this is going to be our t. So this is our t of, this is our t inverse, right? This is t inverse. It's going this way. T inverse of xy. All right, so you need to do a couple of things. I'm going to give you some time to do it. Pause the video, work this out. But here's what you need to do. You need to find a formula for t of uv. You need to figure out where these points go, right? So you need to determine the domain S, and then you need to compute the Jacobian, and then compute the integral, right? Compute your j of uv, and then finally, after all of this, compute the resulting integral. Okay, so why don't you take a moment, work on that, and I'll check back in with you in a few minutes. All right, let's see how you guys did. So first of all, you don't have to do this in any particular order, but one thing that we notice, right, we first can see that the integrand is going to become, at least the portion of the integrand that we can see right now, right, without the Jacobian, but the integrand becomes, instead of e to the x plus y over x minus y, it becomes e to the u over v, okay? And then our boundary points, so I'm just going to write these down. I hope you guys work these out, but the boundary of the integral, it's still going to end up being a trapezoid over in this space, but it's a trapezoid that's bounded symmetrically, right, as follows here. So this point up here is going to be negative 2, 2. This point is going to be negative 1, 1, and then 1, 1, and 2, 2. So this is going to be the domain S right here. So this will be our domain S. Then from there, we can compute the inverse transformation. So the transformation that we want is the inverse of the inverse, right? This one ends up being, I'm just going to write it out because, again, hopefully you guys have worked it out, but t of uv. You just solve a system of equations here. You solve you have a system of equations, I should say, that you want to solve for x and for y. So you add the two equations together to eliminate the y, and you'll see that 2x equals u plus v. So what does that mean for x then? Well, x has to equal 1/2 of u plus v, right? And then if you subtract them, you'll get 2y equals u minus v. So then obviously y is going to equal 1/2 of u minus v. So there's our transformation. And now our Jacobian is going to be determined from this, right? So our matrix j hat, when we take the partial derivatives, these are both linear functions. So our partial derivatives are going to be 1/2 and then 1/2 in the x direction, dx du, dx dv. And then in the y direction, it's going to be 1/2 and minus 1/2, right? And so our function j of uv, which is the determinant of this matrix, is going to be minus 1/4 minus 1/4, right? And so that's going to be minus 1/2. So negative 1/2. All right. So now, how are we going to compute this? So this minus 1/2 is going to go in our integral, right? So what we end up with then is we need to figure out how to integrate this, right? So this one, I've shaded it kind of diagonal here, but to integrate this, we are going to want to treat this as a type 2 integral, right? So a type 2 integral in our S domain here. And so as a type 2, this one's going to be bounded by two lines, right, that we need to have. We're going to integrate in this direction first, in the u direction first, right? So these need to be lines that are written as v in terms of u in terms of v. We want to be left with v as the second integral, right? So they're going to be u in terms of v. So this one, of course, this line is just u equals v, right? U equals v. And this one is going to be u equals minus v. So these are the boundaries. So we go from minus v up to v, and then v will go from 1 to 2 in this direction. So it's going up in this direction. So one of the reasons for the minus sign over in the Jacobian here is that we have flipped. You can see the orientation has flipped, right? It's taken this orientation here where it's kind of almost like the smaller base is on top, and it's flipped it so that the smaller base is on the bottom. All right, so that's part of the reason for the minus sign in the Jacobian. So what we end up with then is the following for our integral. Again, hopefully you guys were able to work this out, but this is going to be e to the x plus y over x minus y dA equals double integral over our new domain S of e to the u over v of the Jacobian j of uv du dv, but I'll just write it as dA in this case right now just for a moment. We're going to do it as a type 2, right? So we need to make sure that it's going to be du first and then dv. And what it ends up being is the integral from 1 to 2 times the integral. So it ends up being the integral from minus v to v, right, of e to the u over v times negative 1/2 times du times dv. And then if you work this all out, what you end up with at the end of the day here is 3/4 e minus 1 over e. So I'll let you guys work out this integral. This is just an iterated integral now, but when you work this out, you end up with 3/4 e minus 1 over e. Okay, so you should need to do it in this order. Everything works out great. So that's that. All right, what we end up with next is, or what I would like to end this with next, is another integral, another example here. So this is going to be number 5. So for this one, let's compute the following. Double integral over the region R, x times y, dA, where R, in this case, is bounded. Of course, these mean nothing without knowing what R is, right? But R is bounded by the following curves. So the lines y equals x, y equals 3x, xy equals 1, that's a hyperbola, and xy equals 3, another hyperbola. So 2 hyperbolas and 2 lines. And let's sketch this first, and then we can write down a transformation. So this is going to be a very crude sketch because we just want to make sure we have some idea here. But let's say, all right, y equals x is this line, right? Y equals 3x is going to be steeper. So I'll draw it this steep. Again, we just need an idea of what this looks like, right? So we'll call that y equals 3x. And then our 2 hyperbolas are going to, if we rewrite these, right? So this is just y equals 1 over x. So y equals 1 over x is going to look something like this. Y equals 1 over x. And y equals 3 over x is going to be, it's going to cut right between this actually, because it's going to be bigger over here, right? So when x is less than 1, 3 over x is going to be actually smaller, right? And then it's going to be bigger over here, and it actually cuts right between those. So you can graph these if you want, but y equals 3 over x. And so they intersect here. And so then the region that we're looking at, this is the key. I'll just kind of sketch it in black here, but it's supposed to be this symmetric region right here. So this is our region R. All right. What we can do then is we can just make a change here where we want to set kind of x times y. We want this to be a slightly different variable. So here's the transformation that we'd like to set. So t inverse here, or I actually, this one's going to be t. Yeah. So for this one, let's use the following transformation. Let's let t, so t, remember, is the transformation that takes in the u and the v and gives us back the x and the y, right? So let's say x is going to be u over v and y is just going to be v. And let's see how this works, right? So in this case, the equations are going to look like the following. Y equals x. This equation is going to become now v equals u over v, or this of course can become u is equal to v squared, right? Similarly, the equation y equals 3x is going to become v equals 3u over v, or u is equal to 1/3 v squared. So there's two parabolas that we're bounded between now. And then the other equation, so x times y is equal to both 1 and to 3, right? But look what happens if you multiply x times y, you get u over v times v. It's just u, right? So u is going to vary from 1 to 3 in that direction. And so our new domain is going to look like this. It's going to be these two parabolas now instead of hyperbolas. So this one will say u is equal to v squared. So in this case, my v's down here and my u's up here, right? The way I've drawn it, because I drew it like a regular parabola. And then the other one is going to be u is equal to 1/3 v squared. So it's going to be a little wider. All right, and then the boundaries are going to be 1 to 3. And so this is our new domain, 1 and 3, and that's in the v. That's in the that's in the u direction. So I've drawn this wrong, right? It's going to be this way, right? So u is going to go from 1 to 3. So we can see now that we want this to be this way. So 1 to 3 in the u direction. Okay, so this one is going to also be a type 2 now, and so we'll want to compute that from here. But basically, I just wanted to write down this transformation, and I want you guys to finish this one. So as a recommended exercise, please finish this integral. All right, by the way, x times y was our integrand as well, so our integrand is just going to be u as well. So this becomes the integral here. So we need to, this is our new s, right? So the integral that we want to compute is the integral s of u times the Jacobian j of uv times dA. So compute the Jacobian and go from there. So I'll leave this one for you guys to do, and we'll call this lecture here.